Next question is about the topic of the fundamental of vibration. Actually, you have studied this topic from calculus, applying for the topic of the second order differential equation. Okay, so then this is the application for second order differential equation. Let's see that this is a spring problem. Okay, we know that we have a spring is stretched 100 millimeter by 20 kilogram block. So this is the for this statement is mean that we the problem give us the constant k. Okay, is not straightforward, but it's give us by using the equilibrium position for this case. Okay, so that's mean that if this is the equilibrium position, right? Okay, so then we have this spring force Fs. Okay, and this is mg. Okay, so then it means that we have mg equal to kx, ky, ys is a static position. So for this case, we have mg is 20 times 9.81. Okay, that's equal to k is a spin constant, and ys is become 100 millimeter. Okay, so then is we may have to divide it by 1000 to convert it to be meter. Okay, according to this, we can find for the spin constant here. Okay, we found that the spin constant is become 1962 Newton per meter. Okay, and according to the spin constant, we can determine for the natural frequency, okay, of this system. This is a single degree of freedom system. That is the omega is equal to square root k over m. Okay, and m is the mass. Okay, and k we already determined it is equal to 1962. And we for this case we found out the natural frequency is equal to 9.9 radian per second. Okay, and if we would like to determine the solution of this problem, okay, actually is you can derive this equation. Actually, y is the solution of the differential equation. It's actually it is the second order, okay, differential equation. For this case, this is m my dot plus ky equal to 0. Okay, this is the solution for this case. Okay, you may find out, you may substitute y this term into this equation. You will see that it is satisfying this equation. Okay, so because we already know that the solution for the vibration, the free vibration of the spring is become this equation, and we have two constants, that is a and b. Okay, and we know that the initial value, initial condition, that is when time equals 0, the problem gives us that the block is displaced 150 millimeter downward from its equilibrium. Okay, from its equilibrium position, and given downward velocity 1.5 meter per second. That is initial value. That is y0 and v0 is equal to 150 millimeter and 1.5 meter per second, respectively. Okay, so then for this case, we have the initial condition that when time equals 0, y0 is become 0.15. Okay, and v0 is become 1.5, and both are downward. Okay, so from this equation, we substitute when time equals 0, we found that y is become 0.15. Okay, from this equation, we can determine for the constant, the first constant, that is b. the constant B is become 0.15 meter. And then after that, we would like to find another constant that is A. Okay, we take the first derivative to this equation. That is to find the velocity, or the first derivative of y is equal to the velocity. And when we take the first derivative to y, that is a sine omega t plus b cosine omega t. And then we take the first derivative, we got a omega cosine omega t minus b omega sine omega t. Okay, and after that, for the initial condition, that is, we know that t equal to 0 and v equal to v0, that's now is equal to 1.5 meter per second. Okay, we substitute this value to this equation. We found that cosine 0 is become 1, sine 0 is become 0, so then the last term is become 0. So we can determine for a now, that is equal to 1.5 equal to a times 9.9045. Okay, so then we got a equal to 0.15145 meter. Okay, so then that's why we complete the equation. We substitute a and b into the equation. We got this, and we substitute omega into the equation also. That is the solution here. And this equation, we can rearrange this equation for some we can rearrange this equation in terms of the amplitude of the wave. Okay, the amplitude of the wave is equal to c equal to square root of a squared plus b squared. That's amplitude of the vibration. This is for this case, we already know a and b. Okay, this is become 0.21316 meter. Okay, and the phase angle for this wave of the vibration, we can determine from the arctan of b over a. Okay, and we got this is equal to 44.72 degree or 0.780959 radian. And then we can have the alternative solution that is come from this equation. Okay, that is equal to 0.21319. This is the amplitude of the vibration, and sine omega t plus 3. That is the phase angle now. Okay, so then the solution is can be written in two forms like this. That is the actually it is a harmonic function. That is composed of sine term and cosine term. You may plot in the graph for this equation also. Okay, and then you will see that what's happened to the position at any time. Okay, so this is the basic case for the fundamental of vibration. As we may have to solve that when we have to consider when we design the high-rise building or the building that is maybe subject to the vibration. Okay, that's we may have to consider this case also. So that is a fundamental problem for that. Okay.